Okay, you guys, so today we're going to talk about the wave equation and do some examples with that wave equation and other standing wave math. So I already talked about the frequency and period in the last video, but just a quick refresher. The frequency is the number of waves or cycles that occur in 1 second, and that's measured in hertz. And then the period is the amount of time for one complete cycle, which in this case is a wave. The equations here, we get period is equal to 1 over frequency, and frequency is equal to 1 over period. So they're inverse of each other. Now, the big wave equation that we're going to be using today, well, one of them is velocity is equal to frequency times wavelength. Notice how velocity, as always, is measured in meters per second. Frequency is measured in hertz, which is really just 1 over seconds. It's cycles over seconds, but cycles isn't really a unit. So it's just 1 over seconds. And then wavelength is in meters. So what we get is meters from wavelength on the numerator in the unit, and then seconds on the denominator from hertz in the unit. So we get meters per second. That's how those units work out. Also, in some of these problems, they are going to be talking about the speed of sound. The speed of sound in air is about 340 meters per second. So that's kind of a hidden given. It's kind of like you should know what that is. I think I give it to you in the first problem, but not in a later problem. So just remember that that's a hidden given in these problems. The speed of sound is about 340 meters per second. I think it's actually 342 meters per second, but it does depend on like the temperature of the air and things like that. So example number 1, we have the lowest frequency sound wave the human ear can hear is 20 hertz. If the speed of sound is 340 meters per second, what is the wavelength of a 20 hertz sound wave? So let's write down our givens first. We have that the frequency is 20 hertz. The speed of sound, so velocity, is 340 meters per second, and we want to know the wavelength, which remember is denoted by that lambda upside down y. So this is just an easy problem because we know that velocity is equal to frequency times wavelength. Since we're solving for wavelength here, we'll divide both sides by frequency, and we end up getting that wavelength is equal to velocity divided by frequency. Now we'll plug in our numbers here. Velocity is 340 meters per second. Frequency is 20 hertz. So we end up getting 340 divided by 20, which ends up being 17 meters. And this is a really long wavelength, right? But it's actually totally understandable for a sound wave. Other waves that can be really big are like radio waves and television waves. Those are actually really big as well. They will have a different velocity though, because they're not sound. They're electromagnetic waves, which we'll actually talk about next week. Example number 2, while at a track meet, you notice a time delay between when you see the starter's pistol fire and when you hear it. If that delay is 0.4 seconds, how far away are you? Have you guys ever seen this actually happen? It is really cool. Maybe not with like the starter's pistol, but I used to watch like the fireworks from really, really far away from the fair because my dad lives up on the hill in Ventura, so you can see the fireworks. And I always remember thinking that was like the coolest thing when I was a kid because you can see the fireworks before you can hear them. And it's because the speed of light is much, much faster than the speed of sound. So very, very interesting. So as always, let's write down our givens. So we know that the time delay is 0.4 seconds, and we want to know how far away are you? So we want to know the distance, right? Now, the other hidden given that I just talked about is that the speed of sound is 340 meters per second. So we want to know the distance, and we know that the velocity is 340. Now, this is kind of a weird problem because I don't get a frequency, I don't get a wavelength. Like, what are they trying to give me here? Well, if you remember, way back in the day, the very first week of this class, that velocity, average velocity, is equal to distance over time. So I'm kind of trying to trick you here because we're still talking about a velocity. And in this case, it's the velocity, the speed of sound, which is a constant velocity. So we are able to use this problem or this equation. So we end up getting that if we're solving for distance here, which is like our displacement, because it's only in one direction, that's delta x, we get delta x is equal to velocity times time. So plugging in our numbers, we get 340 meters per second times the time of 0.4 seconds, and we end up getting 136 meters. So even though you're only 136 meters away from the starter, that's firing the pistol, you're still getting quite a bit of delay. I mean, 0.4 seconds is, you'll notice it, which is kind of interesting. All right, example number 3, we have a wave makes 150 cycles in 30 seconds. If the velocity of this wave is 10 meters per second, what is the wavelength of the wave? All right, so as always, let's write down our givens. We have 150 cycles in 30 seconds. Now, I'm not really giving those a variable yet because we are going to use those numbers to find a variable, and I'll show you what I mean in a second. The next thing that we get is that the velocity of the wave is 10 meters per second, and we want to know the wavelength, so we want to know lambda. So I know that velocity of a wave is equal to frequency times wavelength. Now I have the velocity and I want to know the wavelength, but I don't know the frequency, but I can find the frequency from my other given information. So I know frequency is equal to the number of cycles over the number of seconds. So here I get 150 cycles over 30 seconds. Plugging in that into my calculator, I get a frequency of 5 hertz. Now you've seen that I've already rearranged the equation. I know that lambda, the wavelength, will be equal to velocity divided by frequency. So now I can just plug in my information. I get the wavelength, lambda, is equal to that velocity, 10 meters per second, over the frequency, which is 5 hertz, and that ends up being 2 meters for my wavelength. All right, so let's talk a little bit more about standing waves. Now, I mentioned standing waves in my last video, but I do want to go into it in a little bit more detail and kind of show you guys some math with standing waves. So standing waves, again, to review, standing waves occur when an incident wave and a reflected wave interact. So we get constructive and destructive interference, which causes a resultant wave that looks like it's standing still. So you might get something that looks like this. Now you can see that some of this is already labeled. So I want to go through a little bit of vocabulary with you guys. An antinode is an area with the greatest movement. So here we can see that we have 2 antinodes with this standing wave. A node is an area with no movement, and I remember it because it's node, no, yes. And you can see here that we have 3 nodes. Remember, nodes for a standing wave, we actually have nodes at the ends when both ends are fixed as well, okay, because there are no movement there either. And then last but not least, we call these different harmonics. So the harmonic number will be the number of antinodes. So in this case, we have 2 antinodes, so this will be the second harmonic. Now here's a video of a standing wave demonstration. I usually do this for you guys in class and actually have you do a lab with big, huge springs, but unfortunately we are not in class right now. So I'm just going to show you a part of this video and you can actually see standing waves in action. And I muted it because I was like, we don't need to listen to you talk, dude. Oops. All right. All right, we're gonna have to fast forward this, buddy. Okay. Okay, there we go. Oh, come on. Come on, work with me here, man. Okay, sorry guys. I don't want to re-record all this, so. So you can see here's the second harmonic also. Let's see if he did the first harmonic. Oh, that was in slow motion. Okay, so this is how fast he has to go in order to make this standing wave. Notice how there's an antinode here, there's a node here, there's an antinode here. So that's going to be the second harmonic. I don't know if he did the first. That's the second harmonic. No, looks like he's struggling. Oh no, there's the first harmonic. So this is in slow motion. So see how it's just going up and down? And so you have just one antinode. There we go. There's the first harmonic. Okay, this is also called the fundamental frequency. There's a whole bunch of information about like music notes and things like that with different fundamental frequencies and the first and second and third and so on and so forth, harmonics, and then overtones and things like that. I'm not going to get too much into these things, but we will talk about them more next week. Oh, and here he is making the third harmonic. All right, so you see 1, 2, 3 antinodes. Here's a node here and a node here. Again, nodes at the end as well. And then let's see if he makes any. Oh, look at that one. 1, 2, 3, 4, 5, 6. That's the sixth harmonic. All right, you see the 6 antinodes there. So these are standing waves. So again, what's happening here is this little thing is going up and down. It's creating an incident wave. That incident wave then hits this fixed boundary right here, reflects back, and then you have interaction between the incident wave and the reflected wave, which is causing constructive interference and destructive interference. All right, so that's what a standing wave is. Okay, let's move on. Okay, so I didn't even have to do that. I wanted to talk about standing wave math now. So what I mean by this is we do have a relationship between the antinode or the harmonic number and the wavelength. In these problems, and I have an example of a problem next, okay? So first and foremost, let's just fill out this table. So here's my first harmonic, or again, I call this the fundamental frequency. There is one antinode here, which you can see, remember, that's the area of the most movement. And there are 2 nodes here because we have a node at each end. Okay, everyone see that? Now next, second harmonic is going to have 2 antinodes, and we have 1, 2, 3 nodes, and so on and so forth. You probably kind of see a pattern here, but I am going to go here before we do anything else. Okay, so what we're doing here is I want to see how many of the lengths of string, this is what I mean, this is the length right here, this is the length right here, how many of those do I need to make a complete wavelength? Now here, do you see how I only have half a wavelength here? We don't count this bottom, it's really the string, it looks like it does this, and you can kind of see it in that video that I just showed you, but it's just vibrating so fast that it looks like it's in both places at once, but really it's just up or it's just down. So what I need is another, like this is my crest, I need a trough in order to create a whole wavelength. So I need 2 times that L, this L right here, in order to create a whole wavelength, okay? Now for this one right here, I do have a complete wavelength. Do you see that? So I have a crest and I have a trough. So that's just 1 L. Now instead of putting 1 though, I am gonna put 2 over 2, and I'm gonna show you what I mean by that. You'll kind of see a pattern after a while, okay? And then for the third harmonic, 1, 2, 3 antinodes, and then 1, 2, 3, 4 nodes. And then we can see here, here's my wavelength here. And do you see how this is 2/3 of the length? All right, so my wavelength here is 2/3 of the length. So I'm going to put that here. And then here we get 1, 2, 3, 4 antinodes, 4. And then I have 5 nodes. And then look, you can see here's my wavelength here. And look, I have 2 total wavelengths. So that means that my wavelength is only 1/2 of the total length. So again, I'm going to be a little weird here. Instead of putting 1/2, I'm going to write 2 over 4, which is equal to 1/2. And then you probably are starting to see my pattern over here. And then 5, I have 5 antinodes in my 5th harmonic, and I have 6 nodes in my 5th harmonic. And then we are going, if you see my pattern, we have 2, and then 2 over 2, 2 over 3, 2 over 4. So really this is like 2 over 1. Do you see how it's 2 divided by the harmonic number? You guys see that? Yes? Hopefully. So you end up getting 2 over 5 for the wavelength for the 5th harmonic. Okay. All right. Okay. All right. So example number 4. I already had a preview. We have the string below is 9 meters long and is vibrating as the 3rd harmonic. The string vibrates up and down with 120 cycles in 3 seconds. Determine the frequency, period, wavelength, and speed for this wave. So our givens here, we have the length is 9 meters. It's vibrating in the 3rd harmonic, which means we have 3 antinodes. The string vibrates up and down with 120 cycles in 3 seconds, and we want the frequency, period, wavelength, and speed or velocity. Now, the first two are pretty easy, right? If we want to find frequency, we know it's the number of cycles over the number of seconds. So we get 120 cycles over 3 seconds, which is 40 hertz. We also know the relationship between frequency and period. So I know that period is 1 over frequency. So here I can just divide 1 divided by 40, which ends up being 0.025 seconds. Now, another way you can do this is seconds over cycles, which is what the inverse of frequency, right? 3 divided by 120 ends up being 0.025 as well. So you can use both of those. It's totally fine. Now, wavelength is a little bit more difficult. I did show you the pattern on the last slide. Here, what I like to do kind of in my head is I like to divide this length by 3 because I have 3 antinodes. And I also know that I need 2 antinodes to make a complete wavelength. So if I divide this 9 by 3, I get 3, 3, and 3. And then I know that I need 2 of them to make a whole wavelength. So I get 3 plus 3, which is just 6. So that's my easy way to do it. The other way you can do it is use the wavelength equals blank length, like I showed you in the last one. If you rearrange that as well, you end up getting length is equal to n over 2 times wavelength. Or in this case, since it's the third harmonic, I don't know why I wrote it like this on the slide, you guys, I'm sorry. It would be the wavelength would equal 2 over 3 times L. So 2/3 of L, which in this case is also 6. And then last but not least, we know that the speed or the velocity is frequency times wavelength. So here we get 40 hertz times 6 meters, and we end up getting 240 meters per second. Okay, so that is the standing wave math that you might run into. If you guys have any questions on any of these math problems, feel free to let me know, okay? You can email me at any time. Come to office hours on Friday. I would love to talk to you and see you and interact with you guys as much as possible as we come to a close of this year, okay? Sorry, this lecture was a little bit all over the place. That video didn't want to work for me, so that's okay. All right, I hope everything is well with you guys, and I will see you next time.